Welcome to the lecture 14 of the mechanical vibrations course in the summer of 2024. The discussion today centers around uh, what happens in the energy dissipation for a viscous damper, and then same thing when Coulomb damping is considered, and finally what is called hysteresis or structural damping. Okay. So let's concentrate on the viscous damping before. For the past 6 weeks, we have used viscous dampers where the viscous or the damper force was proportional to the velocity of the damper, Cx dot. And for a short period of time, maybe a lecture or two, we concentrate on a slightly different version, which is the dry friction or Coulomb damping, where that statement is not true anymore. In other words, the damping force is coefficient of static friction times the uh, normal component or the weight of the object, and it doesn't change with time. However, the direction of it will change. For example, uh, we more appropriately wrote it at mu coefficient of kinematic friction mg times the sine means SGN, in other words, the algebraic sign of x dot. But anyway, I'm not talking about that thing right now. I'm looking at the viscous damping where the actual damping force was Cx dot, okay? So what we want to do is during one cycle of oscillation of the mass, we would like to find out how much energy is actually dissipated by this process. And the energy dissipated, of course, comes from the fact that the damper takes it, and therefore, over one cycle is going to be damping force times a tiny bit of displacement. So this is the definition of work. A little bit of work that is done by a force Fd, which stays constant while moving a distance dx, is going to be Fd dx. Work is equal to force times displacement, integrated over one cycle. Now, one cycle in this problem, if we assume that the applied load is harmonic, in other words, the load that's applied to the mass is of the form F naught times, for example, cosine of omega t or sine of omega t. It makes no difference. Frequency is omega. The period is 2 pi over omega. And therefore, this is one cycle, 0 to the period, 0 to 2 pi over omega. The damping force is Cx dot. And dx, I'm going to write it a different way. I'm going to write it as, instead of dx, I'm going to write it dx dt. Notice that we can pretend that these dt's cancel each other out and you still get dx and dx, okay? So, but remember, dx dt is nothing but x dot. So there is Cx dot times x dot, which means Cx dot squared t. Now, if the applied force is harmonic, we figured out that the steady state response is also harmonic, okay? Of the form either x sine omega t or big X cosine omega t. It really doesn't matter. In the steady state, doesn't matter. And I mean, this is the treatment as it's done in Inman. Therefore, I would assume that x steady state is big X sine omega t, that you have seen these things before, okay? So I take this thing and differentiate it and stick it in there and do a simple integration. Remember, the derivative of x sine of omega t is omega cosine of omega t. And then you're squaring it, so omega squared end up in the front. X is also does not depend on big X, does not depend on time, it ends up in the front, and you get this. This is the kind of thing that you did in your calculus class, calculus 2 class, or calculus 1 class, and it's basically integration of cosine squared. And there we use half angle formula, or just look it up in the book. Just look up the integral of cosine of something squared, okay, dx. And we just use the formula. And if you do that, using half angle formula or looking it up in the book, the energy dissipated in one cycle of the motion of the mass is a pi, C damping constant, omega, guess what? It is omega, okay, not omega squared, because when you integrate this thing, it kills one of the omegas, and then there is x squared. This is the energy dissipated by the damper in one cycle of the motion of the mass. A couple of things that notice that it's proportional to the square of the amplitude, and depends also on frequency. Now that makes sense. Imagine that you have a bicycle pump in your hand and you pump it up really fast. Pump it up really fast in a backward and forward manner. Now, how much heat is generated depends on how fast you're doing it, essentially. So on the frequency of the motion. Okay? But this x squared, of course, is not nothing that I can give you physical interpretation. We can just see that it comes out to be x squared. Now let's go ahead and look at the same thing, except that the dissipation is coming from Coulomb damping. In other words, we are no longer saying that the damper force is equal to Cx dot. We are no longer saying that. We have to go back what Coulomb damping did. It says the damping force is a constant, mu damping coefficient, kinematic coefficient of coefficient of kinematic friction times mg, the weight of the guy, except that the direction of it depends on how the motion was taking place. The direction of it is dependent on the direction of the velocity, okay? So, in fact, when we did it, we said that mu mg sgn of x dot, okay? And there is a minus sign in front of it because friction opposes the direction of the motion, okay, in Coulomb damping. All right, so here's what happened. You can see that FD was, ignoring any algebraic sign, which is built into this actually, built into this. We wrote FD, which is right here, okay, right here. The first four terms, 1, 2, 3, 4, is FD, and dx, we use that same trick, wrote it as x dot dt, okay? All right, so there is some similarity between what's up there and down here, but the actual FD is not Cx dot anymore. It is this thing, okay? Now, I want to show you that if you do this calculation algebraically, you will come up with 4 mu mg big X. If the load, for example, if the load is harmonic, I mean, this big X comes from the assumption that the load that is applied is harmonic, and therefore the steady state also is harmonic with the magnitude of X, okay, and sin omega t. Now, it is very easy to see this based on just simple observation, and we're going to do that in the next slide. Now, before I show you this, let me just tell you where we're going with that. So, what we want to do is take our Coulomb damping problem, which results in a non-linear mother of all equations, and convert it to a linear one by saying that, okay, we're going to replace that friction mechanism with an equivalent viscous damper. Okay? And how do we find the equivalent value? Remember, when I talk about the viscous damper, there's a C involved there. So the question, what value of C should I use in order to be able to say, hey, I'm not going to do Coulomb damping, I'm going to do viscous damping. So essentially what I'm saying is that the energy dissipated in one cycle of a Coulomb damping model, which is this, I equate it to the energy dissipated if there was an equivalent damper, which comes from that very top equation on the right hand side. That will tell you what CEQ is. Okay. Now, we'll get to that, back to that in a minute, but I want to show you what is the energy dissipated in one side. Now remember, this mass goes big X to the right, big X to the left. For example, if it goes big X to the right, the friction opposes that. And what is the work that it's going to do by going big X to the right? The value of the friction is mu F, in other words, mu mg. And it goes one big X to the right, so multiply mu F by big X. And then it goes to the left, okay? It goes to the left. The friction opposes it, okay? So it's going to give you another mu F big X and another mu F big X. And finally, it goes back to where it is, which gives you another mu Fx. The moral of the story is that the friction force is constant. The amount that it moves is big X to the right, back to minus X, that gives you a distance of 2x, and back to where it started X. So the moral of the story is that mu Fx plus mu Fx plus mu Fx plus mu Fx, okay? And that gives you 4 mu mg big X. That's what we have here. Now, you can also see that from this diagram. If you plot the damping force versus the position, you can see what happens. When the block is going to the right, the force of friction is mu mg, okay? When it goes to the left, the value of mu mg does not change, but the sign of it will change. Okay. The point is that as you go one cycle over this oscillation, you're going around this rectangle. And notice that it's not a coincidence that the area of this rectangle, the area enclosed in this rectangle, is 4 mu mg big X. That's the width, 2x, times the height, 2mg, and the product is 4 mu mg big X, okay? And this is what I told you a minute ago about what happens when you go one of these. It's going to be mu mg big X. It goes back, there's 2 of those, and then it goes back, there's 1 more. So the total becomes 4 mu mg big X. All right. Now, what if you also wanted to look at the force of what if you wanted to look at the total force, not just the damping force, another force of work of the spring? Okay. So all you have to do, remember, the force of the spring is not only the damping force, friction force, but also kx, okay? So the total force is that sum. And if you look at this diagram here, if this is Fd versus x, and I wanted Fd plus kx, okay, kx, then all I do is you increase this height by k big X, and decrease this height by k big X, so you get a parallelogram instead of a rectangle, but the area of this is still 4 mu mg X. The point is that the work the point is that this spring does not dissipate any energy. It's only the damper, or it's only the friction that dissipates the energy, not the kx. That should be obvious. All right. So let's go back to the statement that we had a few minutes ago. we found the energy dissipated by one cycle if we were going through Coulomb damping for mu mgx, big X. Energy dissipated if it was a viscous damper. These are both under harmonic load, little x of t equal to big X sine of omega t or cosine of omega t. And if I want to find the equivalent viscous damper, I equate these two, right? I say that I'm going to find C equivalent so that this is equal to that. That's what we did. Okay, we equated it, and then we solved it, and there it is. So you can forfeit your Coulomb damping model and make it a viscous damper, but the value of the damping coefficient is right here. I want to emphasize that when you do that, we know now how is the zeta equivalent? Well, it's C over C critical, or C equivalent over C critical. Okay, C equivalent is right up here. You can see that. And C critical is 2 root of mk. We know that from the first 2 weeks. And just plug it in, and you get the equivalent damping ratio is that. Now this is obtained from just plugging it in. Like there's no magic wand of waving and getting this. It's just a matter of taking the C equivalent, putting it in there, and 2 root of mk, and just working it out. Notice that at some point you will end up with, for example, in this expression, root of k over m, which you can call omega m. Okay. Now, so this equivalent viscous damping, it was based on the premise that in one cycle it dissipates the same amount of energy if it was under Coulomb damping model. Okay, so our job was to find a viscous damper so that in one cycle it dissipated exactly the same amount of energy if it was going through a Coulomb damping situation, dry friction situation. Now, why we did all of this is that this was the mother of all equations for a Coulomb damping nonlinear equation. By this trick, we're going to replace it with a viscous damper. So we no longer have this thing over there. We have C equivalent X dot. And then I've divided here by M to get it in the standard form, which you have seen before. You have seen this before, except that this zeta was zeta. It was not zeta equivalent. Okay. So anything we know about that equation we can do. For example, we can write this solution, steady state solution, steady state solution. So big X sine omega t minus zero. Now remember, when you go back to that lecture about harmonic loading, on the right hand side, I wrote it as big F naught cosine of omega t. But in this treatment, unfortunately, Inman decides to go from big F naught cosine of omega t to big F naught sine of omega t. It makes no difference, okay? No difference. It's just that the solution is going to go sine instead of cosine that we had before. Everything else is going to be the same, so let's figure it out. So if you look at big X from 2 weeks ago, 3 weeks ago, was F naught over K, okay? I mean, you go through the same, basically you go through the same process, exactly what you did when you got the big X and theta. And I'm not doing it here, okay? But if you go through it for this situation, we're going to get F naught over K square root, okay, of that fellow over 1 minus R squared, okay? Look, this box requires algebra, just like we found it before. We found big X and big theta, and they were different from this, okay? That's because there, it was not zeta equivalent, it was zeta, it was different, okay? So, for example, this thing came out to be 1 over square root parentheses 1 minus r squared plus parentheses 2 zeta r squared. It was not this. But if you go through the solution, if interested to do that, come with these. One thing you notice that here, if r is bigger than 1, this denominator inside of the absolute value is negative, okay? And if r is less than 1, inside of the absolute value is positive, okay? And although I have not done it, it is possible to show that if r is less than 1, this theta, this phase angle is positive, and if r is bigger than 1, this phase angle is negative, okay? I'm not showing that. It's just a matter of algebra, okay? This theta, okay, theta is positive if r is less than 1, and theta is negative if r is bigger than 1. Now, this did not happen when we treated the whole shebang 2 weeks ago on the viscous damping, okay? I'll leave it to you to go and find out where it is. Remember that theta was not positive or negative. It went between 0 and pi. But anyway, now also notice that this theta does not depend on r. Does not depend on r. When we did this stuff 2-3 weeks ago, theta depended on r. It was time inverse. But on the top, I had 2 zeta r, and the denominator, I think it was 1 minus r squared. The point is that this theta is for a given f naught and mu, there's no r in it. Okay, so this is the main difference between what you're getting now and what we did before. One other thing is that notice that when r is equal to 1, this thing blows up. That never happened when we did it 3 weeks ago, because when r is equal to 1, there was always a term 2 zeta r in the denominator that helped us, okay? So that's another major difference. And here are the differences once again. To be very clear, several differences in behavior approximate phase and amplitude of the response of Coulomb friction compared to the viscous friction are apparent, okay? When r is equal to 1, this denominator becomes 0, the whole thing blows up. That did not happen in viscous damping case, okay? The second one is, notice that the theta, the phase angle is discontinuous because of this plus or minus. That did not happen for us. If you go back to the plot of theta, you went continuously from 0 to pi, and at resonance r equal to 1 was actually pi over 2, okay? It never changed continuously, okay, when damping was present. One last thing is that notice that this whole thing is nonsense if the denominator is under radical is negative. So if under the radical is negative, none of the stuff that you're saying makes sense. So the one assumption is that this denominator under the radical is positive, and that means pi f naught must be bigger than that, okay? If not, this is all off. This doesn't work, okay? All right. So yeah, basically the whole process. Remember that when we did Coulomb damping, at some point the guy stopped. The block stopped, okay, and basically there must be enough force to overside the or to overtake the friction force. If there's not enough force to do that, it's going to stop. Okay? And we're going to do an example. Now, before I actually do this problem, I want to go back for a second or a minute to this slide. Now, notice that the whole idea behind finding an equivalent viscous damper for a Coulomb problem was to take this nonlinear equation and replace it with a linear one, which is down here. Now, this psi equivalent is, of course, there. And I mentioned to you that this solution is linear, and if you're interested, you can use all the stuff that we did when we treated problems of this type, except that psi equivalent was not there, there was psi, in the past 4 weeks, and use those formulas to get to the solution of this problem. Now, there's a caveat though. What I'm telling you is that the solution to this problem is given like that. There is the big X and there is the theta. And if you look at these, this big X and this theta are completely different from what we got when we solved the problem 3 weeks ago. Telling you that this is the solution is fine, but this is not obvious. And when you go to those equations that we derived 3 weeks ago and replace the psi with psi equivalent and do the algebra, because you will see that when you do that, the X that appears on the left-hand side will also appear in the right-hand side, and you have to solve for X. And when you solve for X, you get something that big X, you get completely different. The moral of the story is that this is the solution to that problem, but by no means it is obvious why that is the case. Okay? So, and if I go back here, I hope you can see that, because the big X is also in the denominator here. When we did this 4 weeks ago, psi equivalent was a constant. It did not have the X in the denominator. So don't be fooled. This is not obvious. And that's why I'm saying, if interested, go to Inman and find out all the steps are carried out. You're not going to do that. So let's go back to this problem that we just proposed. We have a spring mass system with a sliding friction, and the stiffness, the value of the stiffness of the spring is given, and it's driven by a harmonic load, which has an amplitude 90 newtons, 25 hertz. So this 25 is omega. This is your F naught. There's your K. The mass is 10. And of course, it says if you assume that the surfaces are unlubricated steel, from Inman, the coefficient of friction is mu equal to 0.3. What we like to do, the amplitude of the steady state solution, in other words, big X. Okay. This 0.3 comes from the table that we had before when we discussed Coulomb friction. Okay, unlubricated steel on steel is 0.3. Now, first of all, we have to make sure that this whole thing that we're going to talk about makes sense. Remember, under the radical cannot be negative. So what was the condition? We needed pi f naught to be greater than 4 mu mg. If that is not holding, then just going this route of equivalent viscous damper is not meaningful. Okay, so in fact you plug it in, you get the mu, m is given to you 10 kilogram, g is 9.81, and f naught is you're given 90. Plug it in, it works, yes, and therefore we can go this route. Now we're told that your driving frequency is 25 hertz, so that's radians per second. The natural frequency, we have K and we have M, we have there, and R is equal to 4.0454, and just plug it in this expression. Plug it in this expression, and you're going to get the value of 0.53 millimeters. Okay. Now remember, this stuff is all coming from the previous slide, values in the previous slide here. Here's another one. It says the mass spring is subjected to a Coulomb damping, so it's sitting. Notice that it's sitting on a surface here. We're assuming that this is dry friction, it's Coulomb damping. The amplitude is 85 and the frequency is 5 hertz, omega is 5 hertz. The system is found to oscillate with an amplitude 75 millimeters. So we know big X is 75 millimeter. And what we like to do is to find the coefficient of dry friction. Okay, so all we have to do is to write the expression between big X and all this other stuff. All right, so these are the things that are given to us. And the mu comes from this equation. Okay, so we know everything else. The only thing that we don't know is this mu. So what I'm going to do is to calculate it using my MathCAD. So first of all, find the omega n, because we need, remember, we need R here, so we need omega n. And R is equal to omega, which is given to you here, right there, 5 hertz, right there, in radians per second. This is what value of R is. And I give MathCAD this equation with all these numbers, say find for me the value of mu, and mu comes out to be 1.282. Now, there's a couple of things before I move on to the final phase of this lecture, which is the structural damping or internal damping. I want to bring something to your attention, and that is, let's look at the force displacement curve for a system with viscous damping. Okay. Now remember, viscous damping means Fd equal to Cx dot. Okay. So, and if there is, of course, the spring present, you're going to assume that Kx plus Cx dot. Now, suppose that our force is harmonic, the force is harmonic, and therefore the displacement x of t is harmonic. So I take this stuff, the solution to x, steady state solution, and stick it in there. This is what we're going to get. Obviously, the derivative of sine is going to be omega cos omega t. Now, I want to do some algebra here. And the algebra is that I want to show you that this f that's written like that can also be written in this form. That may not be quite obvious to you, but let's go ahead and through the derivation. First of all, this cosine of omega t, I can write it as square root of 1 minus sine squared omega t. Agree? So we have no doubt about this, because f is given on the left side. You plug in this x of t in here, you get that, and there's no ambiguity here. So what I'm going to do is this cosine omega t, I'm going to write it as square root of 1 minus sine squared. Now I take this big X inside. If you take the big X inside, the first term is going to be x squared, and then x squared sine squared omega t. But remember, this thing is little x right there. Little x of t is this. So the right hand side is just kx plus c omega squared root of big X squared minus x of t squared, or little x squared. And that's exactly what I wanted to show you. So by no means it was obvious how from here you go to there. So these are the steps that I'm using in order to show you that the forcing, the total force, which is damping force plus spring force is following that equation. And why did I want to do it like this? So what I'm going to do is I'm going to manipulate algebraically this expression. And how do I do that? I can, for example, take kx to the other side and square both sides. So that's one way. Yeah, let's do that. Let's take kx to the other side and square both sides. So obviously you're going to get f squared, and then you get plus, let's see now, hang in there, make sure that this is f minus kx squared, okay? So you get kx squared, k squared x squared, and then 2f times kx, which is here. So, basically after doing this algebra, the square root is going to go away, and there's going to be c squared omega squared x squared, which is down here. Basically, I'm saying that, look, please, take the kx to the left-hand side, square both sides, and do the algebra. You're going to come up with this expression. You might say, well, so what? Well, let me tell you, okay, that this expression, if we look at big F in the plane big F versus little x, this represents the equation of a rotated ellipse. In the plane where the vertical axis is big F, the horizontal axis is little x, represents an ellipse. Okay? And don't worry about these scales. These scales are totally irrelevant because I'm just looking at generic situation here. And the area of this ellipse, this is called the hysteresis loop. And the area of this ellipse can be shown to be exactly this. And of course, you know that because this was the energy dissipated in one cycle of viscous damping. Okay? Now, why is this called hysteresis loop? Because look at it this way. When x increases, f increases. This is the loading situation. But when you remove the load or reduce the load, x does not go back to zero. It goes back on a different loop or on a different path. That's why this is called hysteresis loop. The loading and unloading path are different. Okay, that's why it's called hysteresis damping or structural damping. Okay, and one thing we know for sure, the area enclosed in this thing is actually that expression. Remember, this goes back to the beginning of this lecture. I took a viscous damper and I found the area enclosed in it, and I got this number. Okay. Yeah. So let's go here. Now remember, I didn't take the spring into consideration there, but that's okay. Spring doesn't add any area, basically any energy, because it's the spring is elastic. So if there was no damping, this area would be zero. Hopefully you can see why. If there's no damping, C is zero, right? Now, this is called the hysteresis loop. It's a rotated ellipse when you're dealing with a viscous damper. Okay? Now, why is it called rotated? Why is it rotated ellipse? Because from your high school or from your algebra class, you know that the equation of ellipse looks like this: x squared plus y squared, x squared over a squared plus y squared over b squared equal to 1. But this kind of an ellipse is only the one that's oriented like so. If you add to this expression an x, a y, an xy, like that, if you look at this expression, it looks like so. Something times x squared plus something times y squared equals constant. But if you add to this expression things involving x and y and xy equal to constant, this will be a rotated ellipse, but it's also shifted. Okay, so it's going to be shifted like that. All right. So this is going to be used later on when we talk about the hysteresis damping or structural damping. Okay, and that's going to be coming next. Okay, now we would like to discuss a different kind of damping, which is known as hysteresis damping or internal damping or material damping or solid damping. These are all representing the same phenomenon. Now, it is very common in material science that you do a force displacement curve based on experimental testing or maybe stress strain curve based on experimental testing. When the loading that you apply in a situation like that, it can be static or it can be harmonic. So we're interested in the harmonic loading in this case. And uh, generally speaking, if the material stays in the elastic range and there's no dissipation of energy basically, when you load the material and then unload it, the force displacement curve retraces the original path, or the stress strain curve also retraces the original path. However, when there is dissipation, energy loss, then the loading curve and unloading curve do not actually follow the same pathway, okay? And therefore, we get essentially a situation like this. So loading, unloading, and then loading again. We get this curve, which is called the hysteresis curve, okay? And this is can be attributed to the energy loss in the problem. And the energy loss during this cycle is equal to the area inside of that curve, or inside of that ellipse. So that's why inside of that's not an ellipse, but it looks kind of, you can see where the ellipse in the previous discussion comes from. Now, it is found experimentally that this area is independent of frequency of that harmonic load that you're applying, but it's proportional to the square of the amplitude of the uh, displacement. Okay, and it also depends on how stiff this material is that you're loading and unloading. So another way of saying that is the change in the energy or energy loss in that one cycle is proportional to stiffness, square of the amplitude, and there is this coefficient here which is called the hysteresis damping constant. So uh, this is the expression for a hysteresis damping or material damping or internal damping or solid damping. Okay, now some books they put K and beta together and they call it value H, but Inman does not. Inman leaves it as K times beta, and this beta is the material characteristic, okay, damping constant. Now, in a real experiment, force displacement or a stress strain curve, such as the one taken from this reference, the situation is a bit more complicated. So you can see that it still has that resemblance, but as cycles increase, then of course there is a shift in this. But we're not assuming that situation. We're assuming that over each cycle, you basically get the same curve. Okay, much simpler than what you see there in real life. Now, what we like to do is we know from viscous damping that this energy loss, if this was a viscous damping, the energy loss would be would not be like that. It will have an omega in it, and it will have an x squared. Okay, this is for hysteresis damping that we're discussing, but we know that from viscous damping, the expression for delta E is right here, pi omega is there, so it depends on the frequency, and x squared. So if you equate these two together, we get an equivalent viscous damping number, which gives you the same energy loss as in hysteresis damping. Okay, so we can look at our problem as a viscous damper with the damping value given by that expression. Okay, so the mother of all equations becomes mx double dot plus c equivalent, which is right here, x dot plus kx equal to f naught sine omega t. Remember, it doesn't matter whether you say f naught sine omega t or cosine omega t, but when we solve this problem, we put it, back in lecture 10, I believe, we put f naught cos omega t. Now, we know the solution to this problem. We know everything about this problem, because if I replace this thing with c, we spent 2 weeks on this, okay? So the steady state solution is given by that expression, okay? And we remember from our treatment of viscous damping that the value of big X was given like that, the value of phi was given according to this, and of course zeta was the damping ratio, which was C over C critical, but our C in this problem is K beta over omega. This will be C K beta over omega, and of course R is the frequency ratio. Now, remember that all of these things are valid when the loading to this material is harmonic. Okay, so just keep that in mind. Now, you can plot these things just like back in lecture 10. We plotted xk over f naught. Actually, it was, I think, whenever we discussed the, I can't remember whether it was lecture 10 or not, whenever we discussed the harmonic loading, so mass spring damper system on the harmonic loading, we got a curve like that, but of course here we are plotting it as different values of beta instead of zeta. But there is similarity, you can see that, and same thing over here. This is the phase diagram. These two together, things like that together, is called frequency response function of the problem. Okay. Now, let's do an example. Suppose we have done a testing, and we have found out that for the material that we're using, we get this kind of a force versus deflection curve. Okay, I'll put some units here to tell you what these things represent. This is the maximum amplitude. This is big X. You can see that deflection, maximum X, maximum deflection. This is big X. The slope of this curve is your stiffness, K, and we have to calculate this area. You just count the squares and half a square and quarter squares, and suppose we came up with this number, Newton meter, okay? And this information, this is the data that we got from experiment. Calculate the equivalent viscous damping coefficient for the 2 hertz driving force, okay? And plot this equivalent damping coefficient in this range. Okay, so this was the experiment that we did. It's written here for you. The driving frequency, we are told that is 20 hertz. So we want to get some plot of the response of the system based on the driving frequency that's 20 hertz, or that many radians per second. Well, we counted this, and it's 5. So this is what we know from viscous damping. From material damping. Remember, there's a beta here, there's a k here, there's x squared. Now we equate this to 5. Okay, that will give us the value of beta. Actually, it gives you k beta, but we know the stiffness, so we can find the value of beta. So, or k beta is this combination. That's fine. Now, equivalent viscous damper is given in this discussion that we had a few minutes ago is K beta over omega, okay? And you just plug in the value of K beta and the value of omega, and you get uh, equivalent viscous damper 253. But it also says, okay, plot this thing. This specific value is for 20 hertz. But if you look at other frequencies, you can plot this thing and you get a curve like so. Okay. All right. If we wanted the value of beta, then obviously you need K. But if you do not need the value of beta, you just want the equivalent viscous damper, then it's the combination K beta that's needed, and we know what that K beta is. Based on the observation that we know the area of this loop, and in a material damping or hysteresis damping, this area is actually given by that expression. We know the maximum amplitude, 10 millimeters or 0.01, and it'll give you K beta. And therefore, C equivalent is given to you. If you want beta, then obviously you have to use this value of K and you get the answer. Here's another problem. We have a load of 5,000 Newton, which is, if applied statically to the mass, you're going to get deflection of this. Okay. First of all, as soon as you see that, you know what the stiffness of the spring is. If 5,000 is applied and you get a static load of this, then K is 5,000 over 0.05. That much we know. Okay. Now, a harmonic force of 1,000 Newton is applied. So now we do this, where F naught is 1,000, and at resonance, we get an amplitude of 0.1. Remember, it says that big X, when R is equal to 1 at resonance, is 0.1. That's the other piece of information. Find the hysteresis damping constant. In other words, find beta. That's what it wants. Okay. Okay, so part A says find the hysteresis damping constant. This is a fancy way of saying find beta. All right. And then the energy dissipated per cycle. Okay, we'll do that later. In other words, delta E. Okay. And we also were asked to find the steady state amplitude big X when we are at not at resonance, but 1/4 of resonance frequency, and then the same thing when we are at 3 times the resonance frequency. Okay, let's get going here. These two will give you the value of K, no problem. And then we write the expression for big X. At resonance, remember R is 1, this goes away. So we have big X equal to F naught over KB. That's great, because we know the value of big X is 0.1. We know the value of K, we just found it. And F naught is 1,000 Newton right there. This one, 1,000 Newton. That'll give you the value of beta. That's part A. Now part B says find the energy dissipated per cycle, which is write down the expression for energy dissipated per cycle. Okay, there we are. We know omega, we know big X. We just know big X, it was given to us, and the C equivalent, obviously, just write the expression for C equivalent, which was beta K over omega, and notice that the omegas cancel out, and you get this. We just found beta, K was given in the first line, big X is 0.1, just plug it in, and you're going to get your energy dissipated per cycle. Now we're asked to find the big value of X when R is not 1. R is, remember, omega over omega n. If it's resonance, omega and omega n are the same, R is 1. But it says 1/3 of the natural frequency. Okay, so R is equal to, let me see, how was the statement of the problem? I can't remember. Just 1 second. It says, this is part C. It says the steady state amplitude at 1/4. I'm sorry, not 1/3. It's 3 times. It says 1/4. Okay, so uh, omega is 1/4 of that. So that's why it's R is equal to 0.5. Okay. Uh, all right. So just plug everything else that you know. You know R, there it is. Beta we just found, and you get 0.01, which is 10 times smaller, almost 10 times smaller than the amplitude at resonance. And repeat this thing for 3 times the frequency. So this is 3, the resonant frequency. So this is 3. Just work it out again smaller. So at resonance, we have the biggest, obviously biggest amplitude. Now, the last problem of today is, let me remind you that when you took your fluids course, they told you that the drag force is proportional to the square of the velocity. So it's not really that viscous damping. Viscous damping is the drag or the force is proportional to the velocity. That's the one that we are using in reference to viscous damping in vibrations course. But it says that, okay, suppose that your body moves with a velocity 20 meters per second, experiences we know that from our fluids course. It says in your fluids course, you have seen that the body is moving at moderate speed, for example, 20 meters per second, experiences a drag force proportional to the square of the velocity. Okay, we know that. Find the equivalent in viscous damping for such force for an oscillatory system, and find the resonance sampling. So essentially, we're saying that in fluids, we were told that the force is proportional to the square of the velocity. Okay, what we want to know is find the energy loss per cycle if this actually was the case. So here's what we're going to do. So drag force is proportional, so some kind of coefficient alpha, velocity squared, x dot squared, and our load is harmonic. Suppose that our load is harmonic. Now it's just a matter of finding energy dissipated in one cycle. Okay, first of all, if the displacement is harmonic, we have the velocity, okay, and we have the force, the square of that, so just plug it in, and then we write down the expression for energy loss. So f dx, remember that trick, dx, we write it as dx dt, so we get another v, this is another v, and then essentially we got v to the third power, okay? And if you want to just plug in the values, you're going to get sine cube omega t. Now, let me remind you, when you took your second calculus course, integral calculus, your instructor spent a lot of time doing sine q, integral cosine q, etc. And at that point, you might have wondered, why are we doing this thing? Well, you can see why you're doing it. So if you work this out from a table, you're going to get the answer. This over one cycle, you're going to get this, okay? And uh, remember, one cycle is 0 to 2 pi over omega, but we have put a 2 in the front and doing it over half a cycle. That's why this is half. This pi over omega is half the period, okay, but we're doing double of that. Okay, so you come up with this, all right? And if you want the equivalent viscous damping, this energy, we're going to set it equal to pi C equivalent omega x squared. That was for, right there, that was for equating this to pi C omega x squared. And that'll give you equivalent, and you get this, okay? Now, if you found this, you can find the damping ratio because it's C equivalent over C critical. And it's just a matter of plugging in. There's your zeta. And if you want to find the amplitude, big X, then what you're going to do is at resonance, you set R equal to 1, go to the formula for amplitude, R equal to 1, and you just found zeta right there. Work it out, and you're going to get at resonance, big X, the amplitude of the vibration of this gadget, whatever it is that moving sinusoidally, is at resonance is equal to f naught over k times 1 over 2 zeta. And if you put the value of zeta from here, if you just plug this thing in zeta here, everything is going to be in terms of the things that we have in the problem, namely natural frequency, f naught, and alpha, the proportionality constant. And there it is. Because there is an x here, there is an x there, you clean it up, you get that expression. All right, that's it. Good luck.